a constant. So we pull out a negative r squared, integral 0 to pi of sine squared t dt. Yeah, because we have sine times sine, so it's sine squared. What do we do? What do we do with this?
Power reducing or half angle?
Half angle formula or power reducing formula. So that's going to, 1/2 is going to pop out.
Half times 1 minus cosine.
Yeah, so negative 1/2 capital R squared integral 0 to pi. And then in here 1 minus cosine 2t dt. Because we've integrated sine squared a lot, right? We've done that many times. And then finally, negative 1/2 capital R squared. Let's find the antiderivative now. So the antiderivative of 1 is t. Remember, we're integrating with respect to t, so it's not x, right? It's t. And then the antiderivative of this, minus 1/2 sine 2t. And we're evaluating this 0 to pi. Good? Okay, let's plug in pi first. When we plug in pi, we get negative 1/2 r squared. This is me plugging in pi, then I'm going to subtract what I get when I plug in 0. So plug in pi. Don't you get pi minus, what's sine of 2 pi? 0. So that whole thing is 0. Right? So that's what I get. Negative 1/2 r squared times pi. And then this one over here, when I plug 0 into all this, what do I get? So 0, and then sine of 0 is 0. So this whole thing is 0 times that. Who cares? It's 0. It's gone. So all I'm left with is what?
1/2 r squared.
Negative 1/2 r squared times pi, right? Now we have a little bit of an issue. It's negative. Why is that negative?
Well, does it really matter? I mean, area can't be negative.
Well, when we were doing areas back earlier this semester, remember how when we were above the x-axis it counted as positive and below it was negative? And the reason it did that was because when we did our rectangle, it was height times width, but your height here was a negative number, wasn't it?
Well, the reason, okay, because half of that, I guess we want to call it half that curve is in the negative quadrant. The cosine is negative.
Yeah, this is harder to see. Okay, so first, do you all agree we did have negative areas before?
Yes.
Okay, it's a little harder to see why this one is negative because your brain is wanting to tell you, look, it's above the x-axis, it's positive.
It's the cosine that's negative in quadrant 2, right? Is that what's...
Well, look at the formula. Look at our formula here. Integral alpha to beta. It was g of t times f prime of t dt, right? So as you're moving, right, the g of t is always what for us? Sine?
R cosine.
It's always sine, isn't it? And if you're up here in the first and second quadrant, sine is what?
Positive.
Positive. So this is going to be positive number always, right? On our interval 0 to pi. But what about the derivative? What's the derivative of this? It was also, right? There was another sign in there, but it popped a negative out. That negative was causing the problem. So this right here is always negative, right? What about dt?
That changes.
That does change, right?
Positive to negative.
Remember our dx was always the width of the rectangle? That was always positive, wasn't it? Because x would be changing, it would be a distance. Here, our dt, it's changing, it's always positive, right? So what I'm trying to show you is that it's harder to see why we're getting a negative area like it is here, because here it's obvious that it's below the x-axis. Here, it's just a result of the derivatives that you're getting a negative area. But it's okay, because all we have to do is say, look, if we want to look at this as an area,
It's the absolute
we just take the absolute value of it, all right? And just concede that, hey, look, yes, you could get an area that's negative. It could happen. So if this is the area of half of it, take the absolute value. The area is 1/2 r squared pi. And now double it, right? And if you double that, you get pi r squared. Because that was only the top half. Yes?
Yep.
Okay. Let's move on. Arc length. So let's say that we had a function, old school. This is the traditional function, y is a function of x. We had a formula for arc length. Does it look familiar? Yeah. Integral a to b, square root 1 plus the derivative of y squared. Right? Well, if we switch this to parametric, here's how the formula changes. Now, I didn't really feel like I wanted to go through why the formula changes like this. We can if you want. No? You're okay with just accepting it? Yeah, I'll show you a general picture and then we'll just leave it alone. The idea is that if you have the curve like this and you want to find the arc length, what you do is you approximate the distance between 2 points. Let me do these 2 points right here. Okay, by constructing a straight line segment, so like a secant line, and you draw a right triangle, and then you have that this is dy and this is dx, and then you use a Pythagorean identity to try and figure out what this side is. So this side would be the square root of this thing squared plus this thing dy, squared, right? That would be that length. And then we want to add them all up. But when you take the derivative of x, what's the derivative of x with respect to t? dx dt, dx dt, dy dt. You see how this, there's a little more involved here, but that's basically what's happening, all right? Okay. Awesome. Now we're going to verify that the circumference of a circle of radius r is, what is the circumference of a circle?
Diameter divided, oh wait, no, it's just 2 pi.
2 pi r, right? So we should get 2 pi r here when we do this. So x is equal to r cosine t, y is equal to r sine t, and t, notice my t here this time, I'm going from 0 to 2 pi. I'm going to go all the way around the circle, okay? Go all the way around and give me the arc length. I'm not going to go halfway and double it. I could do that, but I'm just going to go the whole distance. So according to the formula, the length of the arc will be equal to the integral from alpha to beta, 0 to 2 pi, square root of, all right, we have to take the derivative of x with respect to t. What's the derivative of x with respect to t? We did that earlier. Negative r sine t. But then what do we do with it? Square it. So let's square this and put this in here. Don't you get r squared sine squared t? Yeah? Plus, now we need the derivative of y with respect to t, which was r cosine t. But we need to take that and square it and put it in there. So we get capital R squared cosine squared t, and then dt out here, right? This is going to be so obvious.
So you pull out the r squared?
You pull out the r squared, you factor an r squared out, right? When you factor an r squared out of both of these, that r squared can come out of the root as an r, and then come out of the integral. So you get r integral 0 to 2 pi. What's still in here?
Sine squared t plus cosine squared.
Square root of sine squared t plus cosine squared t, which is 1. Right? That's the Pythagorean identity. Yes? So the square root of 1, which is just 1. So this is just 1 dt. What's the antiderivative of 1? T. So this is just r times t evaluated from 0 to 2 pi. If you plug in 2 pi, you get 2 pi r, and you plug in 0, you get 0. So it's just 2 pi r. Isn't that pretty cool? Isn't that really, really fast?
Yeah, can we have that one? So it's a gimme.
Is it gimme?
Is it gimme?
What I think's really nice about that is if you tried to do this without parametric equations, all right, without the parametric equations, here's what you would be doing. You would be looking at this function right here. That would be the top half of a circle of radius r. If you took x squared plus y squared equals r squared and solve for y, you'd get that. And then what you would have to do is probably not even take the first half. You probably want to go, just take the first quarter, and you would want to integrate something like 0 to capital R from here. And then you would have to do square root of 1 plus this derivative squared, right? This derivative squared in here, and then dx. And it would be probably a disaster, or it would be a mess. I can assure you that. It sure as heck wouldn't turn into 1. Okay? So by just changing our perspective a little bit, we can get very easy integrals. And this happens a lot in Cal 3. We have certain problems, they're hard. We just kind of take off our normal glasses, put on a different perspective, and the problem becomes easy, and then we get that answer and convert it back to where we need it to be. All right? Okay, very awesome. I'm so excited that we're doing chapter 9 right now.
With Cal 3, is it more like conceptual that you're trying to learn and the arithmetic?
It's still, you know, integration, differentiation, and
Well, I mean, like, because in Cal 2 or Cal 1, we learn like a whole new arithmetic of doing derivatives, and then here we learn like integration and all that. Like, is that the same?
no, I wouldn't say that. It's still just integration and differentiation. The problem with Cal 3 is that it's in three-dimensional space. So it's sometimes, you know, students have trouble with that. And then you deal with vectors. And so some students have problems with that. And it's just a lot of visualization. Like, here's a classic problem in Cal 3, all right? Just like a problem, I'll just give it to you and you just tell me what you think. Okay, you have a point sitting in three-dimensional space. Let's say the projector. And you have two planes, flat sheets, that intersect somewhere. I give you the equation of the planes. Those two planes have a line of intersection. What is the shortest distance between that point and that line of intersection?
Straight line.
Unless you're on
Okay, so that's the way the problem would be posed as this. Find the shortest distance between this point and these two given planes. So the problem that students have is trying to visualize all of that.
So with that, would you be asking what point of that line of intersection? Because the line
Well, you would have to find the point on that line of intersection that's the closest to that point, and then you'd have to find the distance.
Okay.
Yeah. Now that sounds like it's easy, but I mean, there's a little bit involved. It's an easy question to ask, but it's not an easy question to answer. All right, there we go. That's it. 9-2's done.
Man, you're just
Crazy. 9-3.
everybody.
So look, we might start chapter 10 next time. I'm just kidding.
And chapter 13, and
No, because maybe on Thursday we can just spend a lot of time talking about the final, you know? Reviewing, like actually have part of a day to review. But I won't get through 9-4, I don't think. All right, so now, put the parametric curves and parametric equations away. You have a way of drawing curves using a different sort of method, and you can do calculus with that method. You can do tangent lines, and you can do areas, and you can do arc lengths. There is another way to visualize things happening on flat sheets of paper, and this is called polar coordinates. And you first have to understand that the coordinate system that we deal with right now are called Cartesian coordinates. All right, so Cartesian works like this. If you have a flat sheet of paper, we have the origin, and we always orient this direction out the positive direction of the x-axis as being like the zero orientation. This is the way when we talked about angles in pre-cal, right? We all said, look, this is angle 0, right? And then we start rotating from there. Now, with Cartesian, the idea was, all right, I would like to get from the origin to some point. How do I get there? So imagine you're a person standing on the ground. Okay, so I'm standing here. This is my head. My feet are on the ground. And I'm sitting there and I'm just looking out the x-axis. So here I am standing here. Here's the x-axis on the ground. I'm facing that direction. And somebody's telling me to go to that blue point, right? So Cartesian says the way you'll do it is to tell them first how far to walk out this way. So let's say 4, right? So I'm standing there and I'm going to walk out, a total robot here, walk out 4. 1, 2, 3, 4. Then what? Turn 90 degrees, perpendicular, and then do what?
I wouldn't go like too many steps.
1, 2, 3. Then walk out like 3 units this way, right? 1, 2, 3, and I'm at that point. So when you write 4, 3 in Cartesian, that's telling you your direction in the x-axis and then the direction perpendicular in the y direction, right? Cartesian. That's what we're born. My 7-year-old was graphing points the other day on a homework assignment, and they were doing this thing. Like we're taught from very young age, Cartesian points, right? But that's not the only way to get to that point, right? I could give this robot a different set of instructions. I could say, turn a certain angle and then walk out a certain distance, and I would get to that same point, wouldn't I? Yeah. So instead, I'm pointed this direction. I say, turn by a certain angle, walk out certain distance, right? So this would be, an angle would be required, right? And what we call R, like a radius, would be required. And if you give me an angle and a radius, I can still get to that point. This is polar coordinates. The data that's given to you is not the direction in x and the direction in y. Instead, it's an angle and it's a radius. Understand? So, given a point in Cartesian coordinates x, y, we can convert the ordered pair to polar coordinates. Now, all polar coordinates are written r theta. So they give you the radius and then the angle. So it's kind of like if I'm that robot, they first give me how far I'm going to walk out. So they tell me you're going to walk out 5 units and you're going to turn a certain angle. So I'm going to turn. I don't know if I want to walk out first. I always want to turn first. So turn and then walk. But the way it's written, they give you the r first, then the theta. And the ordered pair, remember in Cartesian, this matters, right? The order here matters. Same with polar coordinates. It's always r first, then theta. So if you flip them, that has a totally, that impacts where you are, right? So what are the relationships that we have? Well, the relationships we have for Cartesian and polar coordinates come from the triangle, the right triangle we create right there, right? If we draw a right triangle, this is r, this is theta, this is x, this is y. This is very similar to that unit circle thing we were doing, or the circle we were doing with parametric, isn't it? Very much connected. But the relationships we have are that x squared plus y squared is r squared, right? And if I solve for r, I just take a square root. So that's where this first one comes from. Also, if I want to know the angle, I just need to take the arctan of y over x. Because what's tangent of theta? Y over x, right? So the arctan of y over x would be theta. So we have that relationship. And then if we are given a polar coordinate and we want to convert it to Cartesian, we have x equals r cosine theta and y equals r sine theta. Those are things that we kind of already developed when we drew our right triangle earlier. So let's try a couple of these. These are very simple, just introduction things here. Let's convert this Cartesian point to polar. And the first one I gave you, I meant it to be tricky, a little bit tricky. Convert this Cartesian point to polar. So let me quickly draw where we are. -5, 4, okay? That is our Cartesian point, yes?
Yes.
All right, let's convert it to polar. So I need r and I need theta.
Aren't you at negative?
Yeah, no, I don't know. I have no idea why I did that. I've checked out, man. I've checked out. I'm already on summer break. I apologize. 1, 2, 3, 4. Okay, I'm up here. I'm in the wrong quadrant.
Yeah, I was looking, I was like.
And you're all, yeah, man, of course that is. I'm talking about my 7-year-old daughter doing it. I can't even do it.
Just remember, the more education you get, the less common sense you have.
I feel that way. All right. So when going from Cartesian to polar, what are the two things we need to know? Theta and r. So let's get r first. What's the conversion for r? R is
5 squared.
square root.
5 squared plus 4 squared.
So we're going to do square root of x, which is negative 5 squared, plus y, which is 4 squared, which is square root 25 plus 16, which is square root of 41. And that's it. It's root 41. Whatever root 41 is. We could get that as a decimal.
That's what we do in physics.
Okay.
Root 41.
Let's do root 41 on the calculator. Let's just get a decimal just to give us an idea of what that is. It's about 6.4?
Yeah, close enough.
6.4. About 6.4. All right. Now, what about the angle? Because we need that also. This is arctangent of y over x. So this is arctangent of 4 over negative 5, which is, now you're going to have to be careful what mode you're in on your calculator, radian or degrees.
This needs to be in degrees.
You're going to give me the answer in degrees?
We should, right?
I don't care what angle, you just need to make sure that when you write it down, if it's a degree, you put the degree symbol. If it's a radian, you're not going to put the degree symbol.
Oh.
You got what? 39 degrees? Anyone else get 39 degrees?
I got negative 39.
Negative 39 degrees? That sounds more like it. Negative 39 degrees.
I got negative 0.67.
Negative 39 degrees. And you got what?
Negative 6.7 radians.
6
Or
point,
no, 0.67.
points. Okay, I was going to say 6.7. 0.67. This would be in radians. So what is my point written in Cartesian form?
Radius 6.4.
6.4. We'll use the decimal, and then
Do we want to use radians or degrees?
it doesn't. Let's use radians. Radians is mostly used.
Negative 0.6.
Negative 0.67. Yes. Wrong. Okay, so let's think about this.
Because it's our cosine.
Look at this. Remember what our instructions are. Let's look at the degree one because I think it's easier to see it. 6.4, negative 39 degrees, right? I'm the robot, okay? I'm standing here. What is it telling me to do?
Go 6.4 units forward at an angle.
An angle negative 39. Which way am I going to rotate?
Right away.
I'm going to go this way, right? Remember, I'm standing like this. I'm facing out that direction. I'm going to rotate negative 39. Isn't that going to take me down here into the fourth quadrant?
Yeah, that ain't
I don't want to be in the fourth quadrant. I want to be in the second quadrant. There's a limit. See, there is a limit to the arctangent in terms of it can give us an answer, but we still need to make sure that our answer corresponds with where we are. Because remember, there's restrictions on the arctan function. So when we're getting negative 39 here,
You need to add
right?
180.
We need to realize that that angle's here like this. This is negative 39 degrees, but we're actually up there. So add 180 to get over there.
Yeah. No, 180, bro. Whatever.
Make sense?
141.
180? Understand that? So add 180 to this,
No, I thought it was saying add 141.
and you get 141 degrees. Now, what is 141 degrees in radians?
You just multiply by.
Multiply by pi, divide by 180.
No, 180. My bad.
Yep.
Yeah.
So if you ever want to convert degrees to radians, you just multiply by pi, divide by 180. What do you get?
2.5.
2.5, so approximately 2.5 radians. Okay, so like I said, I wanted to try and trick you on that first one. That's why I think it's important for you to put the point, draw it, make sure you know what quadrant you're in, and then when you get your answer, 6.4, and then I'll put 141 degrees, and then I'll do it again, or 6.4 and then 2.5. So let's just look at that first one. Does it make sense that that would work? Does this look like you rotate about 141 degrees?
Yes.
And then walk out about 6.4?
Sure.
Yeah, because if this is 5 and this is 4, then obviously the hypotenuse has to be more than that, more than the longest side here. So, yeah, we happy?
So we have to be cautious on what quadrant.
Yes, absolutely. That arctan function is dangerous.
My physics professor calls it an insanity test.
Insanity test?
So we're
Yeah.
always going to start at basically 0 degrees,
Yes, you always start out at 0.
unless they tell you otherwise.
Well, no, that we always orient down the x-axis as 0. What's I going to say? Oh, so now you can kind of appreciate, I think, some of the limitations of our notation. If I just write this down and I say plot this point,
You don't know whether you.
I don't know if that's Cartesian or polar, right?
But usually people would write that in Cartesian, so then they go to 6.4.
Yeah, like if I walk into my, if I walk into my Cal 2 class that's at 3 o'clock today, and I say, all right, everyone, beginning of the class, I say, plot this point, everyone's going to plot that point in Cartesian, right? But if someone asks you now to plot this point, you should ask them what coordinate system you're in, right? Verify, because we don't have like a special like symbol. We don't do anything like sub p or anything like that to like let you know what system we're in. You have to be aware of that in the context of the problem you're working with. We should have a notation, right?
To make it a lot easier.
Now sometimes it's obvious. How do we convert this one from polar, right? How do we convert that from polar to Cartesian? So we need x and we need y, right? So the formula for x is r cosine theta, and the formula for y is r sine theta. And so x will be 3 cosine of 7 pi over 6, and then y will be 3 sine. Oh, I forgot. Today I've got a. Actually, my wife has a doctor's appointment at 11 o'clock that I'm going to meet her right here at the Christa Santa Rosa, right here. So I'm going to go to that and come back. So I'm not going to be in my office from 11 to 12, or whatever I'm normally there for. Not like any of you really ever come by, but just FYI.
That stings a little bit.
Well, the day I leave and I'm not there is the day that 5 of you are going to show up for help or something, right? So, okay, cosine 7 pi over 6. Cosine 7 pi over 6. 7 pi over 6 is right over here. Cosine of that is the x-coordinate. Negative root 3 over 2. So this is going to be 3 times negative root 3 over 2. And then the y is going to be 3. And then now sine of this point is negative 1/2. So times negative 1/2. So this one's easy, negative 3/2. And that one over there, you're just going to leave it ugly like that. Negative 3 root 3 over 2. And you could convert these to decimals, but I'm just going to write it down the way it is. Negative 3 root 3 over 2, and then negative 3 over 2. There you go. This is our Cartesian point. So if we go this far on the x-axis, this far on the y-axis, we will be at the same point as that polar point.
Is this why they write it like that, like r theta, so you could do this a lot easier?
Do what?
Because if you, I don't know, it's just,
Oh, you mean r theta instead of theta r?
yeah.
I don't know why. It's just someone had to make a decision, right? I think you could have valid arguments for both ways.
Blame that guy full of.
Now, just a little side note here. This wasn't in my notes, but like if you go to like Google and you search graph paper, you can get these free online graph papers where they'll print out graph paper for you, right? And you have these like gridded out papers like this,
Or the other ones too.
And then you have calculus graphing paper.
right? Like this. That's a Cartesian graph. That's Cartesian graph paper because everything runs, you know, your lines, your grid lines are going to run perpendicular to the axis or parallel to the axes, right? Now there's something called polar graph paper. Yes, and the way it works is, think about it this way. These vertical lines here are integer increments of x. 1, 2, 3, 4, right? -1, -2, -3. Then y, 1, 2, 3, -1, -2, -3, right? So they're increment values of x and y. Here, with polar graph paper, we're going to have r theta, right? Let's do increment values of r, which would be, r is the radius, isn't it? That would be like circle radius 1, circle radius 2, circle radius 3. So the graph paper would look like this. You'd have these circles, radius 1, radius 2, radius 3, radius 4, and so on and so forth, right? Then increment values of theta, but we all concede that, look, 1, 2, 3, those aren't common angles. So instead, the graph paper will do the common angles instead. So it'll do like pi over 6, pi over 6, 45, right? Like this. The what?
Dartboard is polar graph paper.
In some ways, yes, a dartboard is polar graph paper. All right, so now if we want to do something like this, 3, 7 pi over 6, right? If I want to graph that, I'm going to go to the third ring. So 1, 2, 3, and I'm going to rotate 7 pi over 6, which will put me right there. Make sense?
And if they're drawn to scale, you can lay them over each other in the same spot.
Yes, if those are drawn properly, you could put them on top of each other and you would have the exact same point. So it's kind of a different perspective.
I think it was making one mistake. They also have what Jacob called engineering graph paper. That's where it's like logarithmic units, right?
Uh-huh.
Where it's just
There's all sorts of different graphing paper. There's 3D graphing paper, which my Cal 3 students, I have that for them on their Canvas shell in their files, so you can graph three-dimensionally. Yeah, there's all sorts. Yes?
The polar coordinates, kind of, sort of, how they figured out once you give us longitude and latitude lines.
That's a little different. Longitude and latitude, those come off of what are called spherical coordinates. So you have, in two-dimensional space, you have, in 2D, flat sheet of paper, you have two generally used coordinate systems, Cartesian and polar. In three-dimensional space, you have Cartesian, cylindrical, and spherical are the common coordinate systems that you use. But they're not the only ones. There's other weird ones, but those are the common ones.
pyramids or some crap.
Yeah, I mean, we like spherical coordinates, right? Spherical coordinates are really good because we live on a sphere. You know, we don't live on a cylinder. Like if Earth was a cylinder, we would have cylindrical we would use this cylindrical system more, but we live on a sphere, so we have we use spherical coordinates. If we lived on some sort of weird pyramid, then we would have some pyramid coordinate system. But
Hitchhiker's Guide to the Galaxy, who had like the fun.
Cartesian is like a box, yeah, a cube.
The Hitchhiker's Guide.
Okay, we have 5 minutes. Let me see what I can do in 5 minutes here. All right, so now polar curves. All we've done is, look, here's a point, take it, switch it to a point, right? But what about functions using polar coordinates? So whenever we have an equation that somehow tells us a relationship between r and theta, so r is some function of theta, then we actually have what's called a polar curve. And so here's an example. The first one, r is equal to 3. So that means that your radius is always 3.
It's a circle.
So it's just a circle of radius 3. It's every point that satisfies R is 3. Every point that satisfies that equation. Make sense? So look at in polar coordinates, the equation of that circle is what? R equals 3. Yes? In Cartesian, what's the equation of that circle? X squared plus y squared equals 9, and that's complicated, right? In polar, R equals 3. Simple. And so sometimes it's easier to work with polar because it's simpler stuff. How about this one? Yes, theta is pi over 4. Now, it's every point that lies, on that rotation angle of pi over 4. Every point. The radius is independent, right? Radius isn't in here. So you're going to have that diagonal. Pi over 6 would be like this, right? Pi would be, if it said theta was pi, it'd be the x-axis. Pi over 2 would be the y-axis.
Question, could
Yes.
we make this almost, I don't know if it is the same or they're intermingled. Could you make it almost like R is a function of something, and then theta is a function of something, and you can create like these kind of spirals or possibly like helixes if you add like a third coordinate? IJK. Like kind of like how our parametric.
I think you're talking about 3D though, no?
Yeah.
Yeah, I mean, yes, I mean, we can go 3D, but you're not going to be able to, you can't make this three-dimensional if R depends on theta.
Okay, well, not so much three-dimensional, but like to draw instead of a circle, we like one's dependent on the other, so it makes almost like those hypnotizing squirrels.
Well, look, they're both dependent on each other here. R depends on theta, but you could argue that theta depends on R also, if you solve for theta. And if we graph this, this is what it looks like. Now, I don't have time to get into this one. I'll do this next class, but R is 2 cosine theta. This is what it graphs. Here's 1 plus sine theta. This is what we call a cardioid. Looks like a heart. It's flipped over.
I thought it was a peach.
Then we have this one right here. This one's really cool. I'm going to talk about this next time, but watch this one. I can draw.
Whoa.
There's the roses.
Yeah, there they are. So you can have roses if you like roses. Okay. And then we're going to do, so next class I'm going to talk a little bit about the graphs of polar equations. We're going to talk about calculus on polar. So we're going to take tangent lines on polars. We're going to do areas on polars. No.
Oh, that's it. That's
That's it.
Yes.
Oh, wait, this is 3. Next section. This is 9.3. 9.4 is the areas in arc length. All right, everyone. Have a good day.
So those polar, what do they call them? Polar roses or whatever?